Greetings everyone, my name is João Luiz João Pereira. I am a PhD student at Federal University of Itajubá, located in Brazil, in the state of Minas Gerais. First, I would like to thank the organizers for their commitment and dedication to promote this important event in light of the rough situation we are experiencing. Our work, whose name is a new multi-objective optimization algorithm inspired by Lichtenberg figures applied to constrained mechanical engineering problems, brings the first meta-heuristic registered in Brazil for this Congress. The algorithm is the result of research developed in the Computational Mechanics and Optimization Group, or GEMEC in Portuguese. This presentation is divided into 5 parts. In the first one, I will talk about meta-heuristics and their importance in engineering. Then, I will explain about the Multi-objective Lichtenberg Algorithm, or MOLA. In the third part, I will talk about the text functions used in this work, the ZDT. Then, I will talk about the 3 engineering problems used in, and finally, the conclusion. With the advance of computing and data science, more robust and efficient algorithms have shown more capacity to find optimal solutions compared to classical optimization methods. The meta-heuristics are an exponent of artificial intelligence in optimization problems and are currently the most used tools in complex engineering problems. These types of algorithms are better able to deal with non-linear, multimodal, discontinuous, and with a large number of input variables and objective functions in the same problem. The most common are NSJ2 and MOPSO. According to the no-field-launch theorem, none of all meta-heuristics can be excellent at solving any type of problem. A certain algorithm may be better for a specific application. Still, there is a constant battle in science for algorithms that can deliver better answers at a lower computational cost. Nature is an invaluable source of inspiration for new algorithms. These reasons led to the authors to create a new meta-heuristics in its single-objective version in 2020 and the multi-objective version in 2021, both published in expert systems with applications. The Lichtenberg algorithm is inspired by the physical phenomenon of lightning, which generates luminous figures with tortuous aspects receiving the name of Lichtenberg figures. The formation of fractals in these figures is very common. For more details about the algorithms, see these papers. How MOLA works. The algorithm is purely numerical and does not require the use of theoretic equations for its operation, since the lightning strike modeling uses the theory of diffusion limited aggregation, DLA. In this theory, a matrix of zeros is created with a central unitary element. Then, stochastically a cluster grows and a Lichtenberg figure is created. See the first figure. The Lichtenberg figure is found at each iteration with different sizes and rotations, controlling the population distribution in the search space. In this way, the algorithm is the first to have optimization routines based on population and trajectory at the same time. To improve the algorithm's exploitation capability or precision, a second Lichtenberg figure with same center point and rotation but smaller size can be created. See the small and red Lichtenberg figure in central figure. Each point in the search space evaluated in the objective functions of the problem generates a point in the objective space. These points are compared using the Pareto dominance relationship, and the dominant solutions are excluded. Any of the decision vectors of the solution that remain, that make up the Pareto front, are candidates for triggering the Lichtenberg figure for the next iteration. See the last figure. The MOLA has 7 parameters. The first 3 are used in DLA, being RC, the equation radius, MP, the number of particles that can be in the cluster, and the stickiness coefficient S, which controls the density of the cluster. Pop is the number of points in the cluster to be evaluated in the objective function at each iteration, black dots in the central figure. Ref is the rate that reproduces a Lichtenberg figure at a ref rate lower than the main one, forcing half of the pulp to stay in it, the red one in the central figure. M is a parameter that controls whether the optimizer creates a Lichtenberg figure. If 1 uses the same Lichtenberg figure in every iteration. If 2 creates one at each iteration. If 0, it loads an optimized Lichtenberg figure with optimal RC, MP, and S values. Then, MOLA will be applied in the first 3 test functions of the ZDT suite. The equations are in this table. The ZDT1 function has a convex Pareto front. The ZDT2 concave. The ZDT3 has a Pareto front with several convex segments. Having diversified Pareto fronts, this set of test functions is one of the most popular in the validation of neural algorithms in the world. In order to compare, NSGA2 and MOLA will also be applied to these functions. Here we have the Pareto fronts followed by the 3 algorithms. In the case of multi-objective optimization, 2 qualities are required of the algorithm: convergence and coverage capacity. The first refers to the ability of the algorithm to approach the ideal point, and the second is the ability to diversify and space the solutions found. It is clear that MOLA performed better than NSGA2 in the 3 test functions and had equivalent results to MOLA in the first 2. On ZDT3, MOLA had more difficulties in having coverage, where MOLA did better. Validated, MOLA will be applied to 3 design optimization problems. The equations of these problems and the search space intervals for each one are in the paper. The web beam design has 4 variables, where H is the weld width, L is the weld length, T is the depth of the beam, and B is the thickness of the beam. The objectives are to minimize the total cost of the project and the deflection of the beam. The problem has 4 constraints. In the 4-bar truss design problem, the structural volume and displacement should be minimized. There are 4 design variables related to cross-sectional area of members 1, 2, 3, and 4. This problem has no constraints. The disk break design has 2 objectives: to minimize the stopping time and the mass. There are 4 design variables: the inner radius of the disk, x1, the outer radius of the disk, x2, the engaging force, x3, and the number of friction surfaces, x4. The problem has 5 constraints. Here we have the Pareto fronts found and the MOLA parameters used. It's possible to see that the algorithm found many solutions with good convergence and coverage capacity, almost overlapping the 2 Pareto fronts. From then, decision-making techniques such as TOPSIS can be used to select relevant solutions, as they are all optimal. The main purpose of this work is to rule the first multi-objective meta-heuristic registered in Brazil and the first hybrid in the world, in the best knowledge of the authors, and show that it can be successfully applied to engineering problems. Still, its relative results as good or even better than 2 of the most used algorithms in the world, the NSGA2 and MOLA. Thank you very much for watching this presentation. I hope you enjoyed it and I am available for any questions.